Alright, so welcome back to another classical mechanics video. At the end of the last video, I said that we're going to look at energy and energy conservation in this video. However, that was a lie. I actually skipped free fall with linear and quadratic drag. So let's look at that. So for linear drag, we're going to have the same sort of scenario as in the last video, an object that is launched at some initial velocity at an angle theta made with the horizontal. But this time, instead of gravity being the only force, we're also going to observe a drag force, which is going to oppose the velocity. So it's minus lambda v. And by the way, this tells us that lambda must have units of kilograms per second in order to make the units on the left-hand side equal the units on the right-hand side. All right, so the first thing that we should do is to write down Newton's laws along both directions. So along the x direction, we're going to have mx double dot is equal to only one force along the x direction, which is minus lambda vx, or minus lambda x dot. And along the y direction, we're going to have y double dot is going to be equal to minus mg minus lambda vy, which is minus mg minus lambda y dot. All right, but we can divide both these equations by m, and the first equation is going to become x double dot plus lambda divided by m x dot is equal to 0. And the second equation is going to become y double dot plus lambda divided by m y dot is equal to minus g. Here we're going to define lambda over m to be equal to 1 divided by tau. Now, why do we do this? Well, the units of lambda over m be the units of lambda divided by the units of m. Well, the units of lambda are kilogram per seconds, so this comes out to be 1 over seconds. And tau is called the characteristic time, and it's also going to have units of seconds. So this top equation becomes x double dot plus 1 divided by tau x dot is equal to 0, and the second equation becomes y double dot plus 1 divided by tau y dot is equal to minus g. Now we're going to go ahead and solve these differential equations. Now a trick for solving DEs is that here in these differential equations we don't see the actual function showing up anywhere. We have x double dot and x dot. So instead what we're going to do is actually solve for v first. So we can rewrite the first equation as vx dot plus 1 over tau vx is equal to 0. And now we can guess that vx as a function of time is just some exponential. So we're going to use the method of undetermined coefficients here. Plugging this in, we're going to have r e to the rt, right? This is the first derivative, plus 1 divided by tau e to the rt is equal to 0, which tells us that r is minus 1 over tau. So vx as a function of time generally is a e to the minus t divided by tau. Here the exponential is unitless. Tau has units of seconds and time also has units of seconds. Now we can go ahead and write down what our initial x velocity is, and from the last video we know that is v naught cosine of theta. So this is going to be equal to v naught cosine of theta e to the minus t over tau. Here's vx. If you're not familiar where the initial velocity came from, go back and watch the last video. Now to solve the second differential equation, we actually have to do one extra step. So rewriting it, we're going to have vy dot plus 1 divided by tau vy is equal to minus g. Now with this sort of differential equation, we actually have to break it into two parts. So the first part is the homogeneous part. So vy dot plus 1 over tau vy is equal to 0. This is the same differential equation that we just solved, so the solution is going to be vy is going to be a general constant of integration, but we can't plug in our initial conditions yet. We need to now solve the non-homogeneous part. So vy dot plus 1 over tau vy is equal to minus g. Minus g is a constant, so I'm just going to guess a constant. So we're going to guess that vy is equal to a constant b. Well, the first derivative of this constant is 0, so we have 1 over tau b is equal to minus g, so therefore we have that b is minus g tau. So the full solution for vy, generally speaking, is a constant times e to the minus t divided by tau minus g tau. Now we can plug in our initial conditions. So vy at time is equal to 0 is going to be a, because the exponential is going to give us 1 if we plug in 0, minus g tau is going to be v naught in the y direction, which tells us that a is v naught in the y direction minus g tau. Therefore we have that vy as a function of time is going to be v naught in the y direction, which we remember to be v naught sine of theta, minus g tau, e to the minus t divided by tau minus g tau. So there's v naught as a function of time and vx as a function of time. A cool thing to look at is the units, right? We want to make sure that each term has units of velocity. So v naught, of course, has units of velocity. Does g times tau have units of velocity? Well, g has units of meters per second squared, tau has units of seconds, so we're left with units of meters per second. All right, good. And for vx, of course, v naught has units of meters per second, so everything has the correct units. Good. Now, if they didn't have the correct units, then we know we would have messed up somewhere. Another interesting thing to look at is what happens after a long time. So the limit as time goes to infinity of Vy as a function of time is going to give us what? Well, this exponential here is going to make all this go to 0. So we're going to be left with minus g tau. And in fact, we're going to call this the terminal velocity. Now, tau is m divided by lambda. If the friction is significant, if the friction is very large, then lambda is large, so tau is small. The terminal velocity will be small, which makes sense. And the mass will reach it quickly because the exponentials will decay to 0 faster. And that should also make sense. All right, now we can find x of t and y of t by integrating these equations and plugging our initial conditions. I'm just going to go ahead and write them down. So x as a function of time is going to be v naught cosine of theta times tau times 1 minus e to the minus t over tau. And y as a function of time is going to be minus gt tau plus tau v naught sine of theta plus g tau 1 minus e to the minus t over tau. So here's x of t and y of t. And of course, you can go through and check yourself. All these terms have units of meters. I'll just check the first one here. We have g times tau, which we know has units of meters per second, times t, which is seconds. So this has units of meters. All right, now looking at the behavior for very large time, we find that the range in x is actually finite, right? So if I take the limit as time goes to infinity for the x equation, we're going to be left with v naught cosine of theta tau. Now this makes sense because the friction is expected to suppress any motion along the x direction. That's how it works. And so the range should be larger if the initial velocity is larger or if tau is large. Now also for large time, y at t becomes linear, right? So as time goes to infinity, this y of t equation is going to become what? It's going to become approximately equal to minus g tau t. And this is logical because the velocity along y approaches the constant terminal velocity. Good. So this all makes sense. Our solutions make sense. We're good. Now the next case we're going to look at is quadratic air resistance. To simplify this problem, we're just going to assume there's no initial velocity along the x direction. But after this, I encourage you to go through a case in which there is both motion along x and y direction, or maybe just motion along the x direction. So we're going to draw our y-axis down to make things simpler, and we're going to have a mass that's falling. So it's going to be subjected to two forces. Gravity, which points down, and because down is the positive y-axis, the force of gravity is going to be positive mg in the y-hat. And then we're going to have force of drag, which is pointing up. So this is going to be in the minus y-hat. But this is going to be equal to minus mu times y dot squared. All right, so because there's no motion along the x direction, we're just going to go ahead and write Newton's laws down for one axis. So m y double dot is going to be mg minus mu y dot squared. Dividing by m, we get y double dot is equal to g minus mu divided by m y dot squared. Here, mu divided by m does not have any units of time, so we're just not going to worry about renaming it. Now, of course, we can do what we did in the last problem and relabel this as v dot y is going to be equal to g minus mu over m vy squared. Now, we actually expect the mass to reach a terminal velocity, as we just found. So we can find what that terminal velocity will be in order to simplify this notation. So when t is very large, we will have what? Well, we will have the acceleration is approximately going to be 0, right? It reaches terminal velocity. So the left-hand side here is going to be 0 at large t. So this is large t. And 0 is going to be equal to what? G minus mu over m. And of course, at this point, we've reached terminal velocity, v infinity squared. So this gives us a formula for v terminal, which is the square root of mg divided by mu, if we do some rearranging. Now, physically, this all actually makes sense. The friction coefficient mu is large, then the terminal velocity will be slower. It should reach terminal velocity quicker. We can now rewrite the differential equation as v dot y is equal to g times what? Well, it's going to be 1 minus v squared over v infinity squared. All you have to do is rearrange this equation here. Now we can use separation of variables. So we're going to integrate from some initial velocity, we'll call it 0, to some arbitrary velocity v of dv divided by the entire thing in parentheses. 1 minus v squared over v infinity squared. And this is going to be equal to the integral from 0 to t of g dt, which we know to be gt. Now this left-hand integral, you can make a change of variable that u is v divided by v infinity, do some rearranging, and what you're going to find is that the velocity as a function of time is going to be the terminal velocity times hyperbolic tangent of gt divided by v infinity. Now this hyperbolic tangent looks like this, where this is 0 and this is 1. And this is minus 1. So we see that as t goes to infinity, we're going to get that the velocity reaches terminal velocity because this function here will go to 1, which is exactly what we would expect. All right, so that's it for linear and quadratic air resistance. As I said, I encourage you to go through an example of quadratic or linear air resistance that's maybe more complex. For quadratic, I highly encourage you to do an example along the x direction or maybe combining both axes. Now in the next video, we actually are going to get into energy and energy conservation. All right, thanks.